Hello, welcome to the NPTEL video course on advanced characterization techniques. Myself, Dr. Kishanu Biswas. This course will be designed by myself and one of my colleagues in the Department of Material Science Engineering at IIT Kanpur. So, at least 20 lectures of this course will be delivered by me and the remaining 20 will be delivered. So, you can see that in the next slide the outline of the course which is given. This course contains different advanced characterization techniques. First one, advanced diffraction techniques, includes small angle X-ray diffractions, small angle neutron scattering, low energy electron diffraction, read and as well as XAPS. Second one, which is again advanced surface characterization techniques exclusively for X-ray photoelectron spectroscopy, Auger photoelectron spectroscopy and secondary ion mass spectroscopy. So, therefore, these two sessions will consist of 20 lectures. Second part of the course consists of mostly microscopic techniques and the spectroscopic techniques. So, when the microscopic techniques, we are going to discuss in detail about transmission electron microscopes, including high resolution, high angle annular dark field imaging, STEM, in situ microscopic techniques like in situ SEM and in situ TEM, electron backscatter diffraction, AFM, that is atomic force microscopy, STM, that is scanning tunneling microscopy, as well as laser confocal microscopy. This will be delivered by me and I am going to start the first lecture of this in the next one. And the last part of the course is basically on advanced spectroscopic techniques, which are very important nowadays for research on nanomaterials and many other things. This includes visible, ultraviolet, Fourier transform, infrared, Raman spectroscopy, as well as in the microscopic techniques the STEM, electron energy loss spectroscopy. So, therefore, this course basically talks about the advanced characterization techniques. So, to understand this course, one needs to know the basics of the normal characterization techniques. That is why the course requirement for this kind of course must be the basic knowledge on the basic material characterization techniques, and this kind of course is already been developed by Dr. A. Sankaran from IIT Madras and Dr. Vijay Agarwal of IIT Roorkee as a web course as a part of the NPTEL lecture series. So, whatever discussions I am going to do for the different characterization techniques has lot of inputs from this material characterization course by two of our colleagues. So, now we shall discuss the detailed lecture wise breakup of this course. This is basically required to tell you that how the different lecture modules will be developed. So, first lecture, which is today, I am going to talk about relevance of advanced characterization techniques for materials development. Basically, these are required for scientific understanding of the different phenomena in the material science engineering. Then the next two parts, that is advanced diffraction techniques and advanced surface characterization techniques. The detailed lecture wise breakup is shown in the slides and this will be discussed by Dr. Gautama in different lectures. So, I will straight away go to the last two topics. In the advanced microscopic techniques, first lecture of that will be devoted on electron material interaction. This will be followed by 4 lectures on transmission electron microscopy, mostly on high resolution and other allied techniques. Remaining 2 lectures will be delivered on SEM related things like in situ SEM and the electron backscatter diffraction. Whereas atomic force microscopy and scanning tunneling microscopy will be dealt in 2 lectures, and lastly the laser confocal microscopy will be discussed. In the advanced spectroscopic techniques, 7 lectures will be delivered on electromagnetic spectroscopies, mostly UV visible and photoluminescence spectroscopy, infrared spectroscopy, and also the Raman spectroscopy. Last lectures of this course, last 3 lectures of this course will be delivered on scanning transmission electron microscopy related spectroscopic techniques, that is EELS and EDS. That will sum up 20 lectures in these 2 techniques. Well, as any other course, we need to have some reference and the books. So, in these slides I am showing you some of the important books. These are not exhaustive, there are many other books available in the libraries or even the market, but I am listing down the most important ones and the ones which I am going to use, and Dr. Gautama also going to use for his lectures. The first one is the material characterization techniques by Zhang, Li and Kumar. It is published in 2008, which will talk about all the characterization techniques in brief. Second one is basically on transmission electron microscopy by Williams and Carter. Third one is on modern ESCA, the principles and the practice of X-ray photoelectron spectroscopy by Burr from again CRC Pace. Fourth one is on scanning electron microscopy and X-ray microanalysis by Goldstein and others. Fifth one is on advanced techniques for material characterization. It is basically a monograph by the Material Science Foundation, edited by Tyagi, Roy, Tulsestra and Banerjee. All the techniques can be easily obtained, or rather can be easily accessed in an encyclopedia called Encyclopedia of Material Characterization, edited by Brundle, Evans, Wilson, published by Butterworth, Hinman, Boston, and this is a very exhaustive book. So, therefore, I will not prefer you at the beginning to go into the encyclopedia, rather than concentrate on the different books on different subject matters. Obviously, first lecture is on relevance of the characterization techniques. So, giving you an idea of the course structure and the modules, I have to now discuss why one needs to study such a kind of course. Those of you who have some idea about the characterization must have seen different characterization labs in the different parts of our country coming up as a part of schemes by Department of Science and Technology, and many cases even by other allied organizations. These centers are actually called characterization centers. There are centers in many IITs, even in IIT Kanpur, IIT Madras, Indian Institute of Science Bangalore, NCL Pune and many other places, where in one roof all the different characterization techniques are housed. So, therefore, you have those of you who have visited these places have got some idea about the different sophisticated characterization tools are used for characterization of materials. So, I am not going to discuss the way the characterization techniques can be used, rather I will give you some examples from our own study where characterizations were used by our own students to understand the material science phenomena in different processes and also to process different kinds of material. These are all done by our students. So, therefore, these are all taken from my own research group, and most of these works are done on very small size particles like nanoparticles or nanomaterials. So, I will one by one I will illustrate you that how important it is to use characterization techniques. Before that, I would like to tell you that in the last 10 years there is a huge improvement in the characterization techniques as far as the limits of the use of this instrument are concerned. One of the example is the high resolution transmission electron microscope. In late 90s, even at the beginning of the 21st century, the resolution limits for transmission electron microscopy used to be in the Armstrong level, that is above 1 Armstrong. But because of the advent of new technologies, especially the aberration corrected microscopic technologies, we could have very high resolution. We can reach resolution of 0.6 Armstrong. So, this barrier of breaking the resolution level below 1 Armstrong was possible only because of the technological advance. And I will show you in some of my lectures how these microscopes can be used to decipher different structures and also the understand the problems of material science. So, let me give you the examples. The first example is on deposition of nanocrystalline copper coatings by pulsed electrodeposition technique. We know that nanocrystalline copper is very important, because nowadays in the electronic industry the connectors are normally made by copper. Previously those connections and the vias used to be made from gold or aluminum or tungsten, but technology has seen a rapid change, because copper can be easily deposited in those positions of the semiconductor devices where the connections are required. So, basic requirement for those kind of connections are very strong and very good electrical conductivity of copper. Not only that, the brightness of the deposits by the electrodeposition should be also very good. These requirements can only be satisfied if one develops a nanocrystalline copper deposits by using a special technique called pulse electrodeposition. This is here shown in the slides. What you can see is a first one is basically showing you the pulse electrodeposition technique, where current is plotted as a function of time. In this case, we use pulsed current for about 8 millisecond, followed by no current supply for about 30 milliseconds. That means the T on, the current is on for only 8 millisecond, followed by T off of 32 milliseconds. Then again the current is on for about 8 milliseconds. So, therefore, by using this pulsed current cycles, one can deposit this kind of nanocrystalline copper. I will not be able to go into detail of this deposition technique, except to show you that this can be done in a normal electrochemical cell, double wall cell, where anode is a copper and cathode is basically a stainless steel 304 grade. So, therefore, if we apply a current when this whole both the electrodes are dipped into a copper sulphate sulfuric acid solution at about 303 degree Kelvin, one can see the depositions of copper from anode to the cathode taking place, and by that one can deposit different copper of different thickness on the stainless steel substrate. The reason for using stainless steel is that it is easy to peel up the copper film from the stainless steel substrate. To give an example how this deposition is done is shown in this case. Normally, if we deposit copper using pulse electrodeposition technique, we do not get nanocrystalline grain sizes. So, therefore, many cases we add different additives, and these additives can be anything like PEG, polyethylene glycol, or any other sulfur compounds like thiourea. Thiourea is most notably used because it is nothing but a sulfur containing compounds, and these sulfur containing compounds can change the deposition kinetics so and so that it is possible to develop the nanocrystalline copper grains in the deposit. The reason for this was not known. People have seen this happen but why and how the thiourea is affecting the deposition process, so that nanocrystalline copper again can be obtained was not known. So, one of our students in my research group started looking at this problem and found several interesting observations to understand the effect of thiourea on the deposition of nanocrystalline copper on 304 stainless steels. First, I will show you two SEM pictures, scanning electron microscopy images of the thin film deposited on stainless steel substrate. The first one is deposited when there is no thiourea. So, you can see very discontinuous deposits, and obviously using laser scanning profilometer one can measure the roughness to characterize quantitatively how rough the deposit, which is shown on the right side of the picture. You can clearly see that the roughness is very high. Some cases mean roughness can be order of several tens of micron. So, therefore, if you do not add thiourea, deposits are very discontinuous and also rough. On the other hand, if you add very small amount of thiourea, about 36 milligram per liter, deposits become very smooth. One can see in the picture here, deposit is very smooth, and also if we measure the surface roughness, roughness is very high, sorry, very low. So, that means roughness can be easily controlled by the thiourea addition, and this is what required when the copper is deposited on any kind of PCB board or visors in the electronic circuitry. So, this was observed very nicely by using a scanning electron microscopic technique followed by laser surface profilometer. These two are the advanced characterization techniques used in many cases. The common idea of deposition model is this. This will help us understanding how thiourea actually affect the deposition process. So, when there is no thiourea, obviously substrate will have lot of surface steps on this like any other surface, and the copper ions will move to the different places of the substrate. Most notably, the copper ion will be able to move on the high or on the crest of the surface instead of tufts here. So, thereby depositing on the crest and making them thicker and thicker and creating deposits, the one which I have shown you, which is kind of discontinuous on the surface. If we add thiourea molecules into the deposit or into the electrolyte rather, the thiourea molecules will basically gets deposited on the surfaces of on the crest, and that's how they will not allow the copper ions to go on this crest. Instead of they will be forced to go on the tufts here, and because of that the tufts will get filled up and we will form a very continuous deposit, so that roughness can be reduced very easily. This is the common idea which is been reported in the literature. But knowing this, does it happen in the actual sense? To do that, we have done a very careful spectroscopic analysis using a scanning electron microscope. The picture here shows the scanning electron microscopy image of the copper deposit, in which there are two large and also very something which is protruding out of the surface of the deposit. If we do EDAX analysis, that is the energy dispersive spectroscopy analysis attached to the SEM, which is nothing but a spectroscopic technique using electron beam, one can see the presence of sulfur peak very easily coming from the surface. Not only that, one can even further analyze this using the EDAX mapping. If you do EDAX mapping on the whole surface, you see sulfur is basically segregated on the surface. Remember, the sulfur is a part of the thiourea molecule, and this thiourea molecule is formula is given by NH2 whole 2 CS. So, therefore, sulfur is obviously is part of the molecule. So, wherever we see sulfur, we can assume that thiourea is present there, because copper does not contain any sulfur. So, that is why you can say that the model which has been developed by different scientists can be proved by different kinds of spectroscopic technique. If you see on the copper MAC, it will be uniformly distributed on the whole surface except the position where there is a protrusion, which has been can be mapped very easily using the scanning electron microscope image. Not only that, one can go on use different other techniques. This one is called transmission electron microscopic technique, which can be used to know the fine scale structure inside these deposits. The left one is showing you the transmission electron microscopic image in the bright field mode of the sample deposited without addition of any thiourea, where you can see that very large grain. This bar is a micron bar, 1 micron. So, grains are very large of the order of 2 to 3 micron, and they contain a lot of dislocation inside it, which are marked by these white arrows. On the other hand, if we add thiourea of 36 milligram per liter, we can see the grain size is extensively reduced from micron size to nanometer size. If this much length is 50 nanometers, so most of the grains are less than 100 nanometer size. So, this really tells us thiourea affects the grain size reduction process. In fact, one can also see the defect structure inside this grains are not dislocations only, but also twins, notably twins, and this is shown in the inside picture here, which shows large number of twins on the inside the grains. So, therefore, thiourea not only affecting the deposition process per se, but also affecting the microstructure, which can be only understood using transmission electron microscope, which is having which is one of the best techniques available to understand the fine scale microstructural features. One can also add up to this story much by using high resolution electron microscopy, which will be part of the syllabus of this course. Here I am showing a one small grain approximately 40 to 50 nanometer diameter, and if we look at in high resolution mode, one can see the twins which are there in the grain, and these twins can also be seen here on this bright field micrograph on the left side of my slide. On the right side, basically it shows a high resolution microscopic image telling you the twins are not incoherent, rather coherent twins, and these are also been reported in the literature. These twins increases the strength of the material extensively. So, therefore, whole process, as you have seen, different techniques were used to decipher the different aspects of the deposition process. In fact, the role of thiourea can be easily brought about by this technique. These are all published literature, so one can access very easily from the literature. So, I am not going to tell you about details of that, but very easily by searching our names you can find out the literature. In fact, to probe that thiourea really affects the grain size reduction by pinning the grain boundaries of the copper grains, we need to use a special technique known as energy filter imaging, which is normally used and attached to the electron energy loss spectroscopy. I am going to discuss in this technique in detail in subsequent lectures, so I will not talk about the technique per se, but I will show you the effect or use of this technique in understanding the whole process of deposition. The left side of the image is basically a normal wide field image taken by transmission electron microscope. Right side of the image shows you the sulfur energy map. In fact, in electron energy loss spectroscopy, you can select the energies of an element which are given as a edge, energy edge. Here we are using sulfur energy edge to image, and we can see this white contours which are present along the grain boundaries, signifying the sulfur. So, therefore, sulfur or rather thiourea is getting deposited at the grain boundaries of copper, and thereby pinning the grain boundaries, not allowing the sulfur the copper grains to grow. This is equivalent to saying that copper's grains are actually capped by the sulfur or thiourea molecules, and thereby they cannot grow further, remain in the nanometric regime. This is another special techniques, advanced characterization techniques, which allowed us to understand the whole deposition process. Next illustration which I am going to talk about is again from our own work, one of my students' research work is on in situ technique. In situ techniques are very important nowadays, especially in situ inside any microscope, either a transmission electron microscope or scanning electron microscope or even atomic force microscopes, are very popular nowadays. In fact, there are conferences on in situ microscopic techniques. So, in situ is a big part of the whole advanced characterization techniques. We are going to show you some sort of view that how this can be used to understand the phase transformation in the nanomaterials, or most notably alloy nanoparticles. So, I am going to talk about melting and behavior of these nanoparticles inside a microscope, okay, so that you can get a feeling that an advanced characterization technique can be done. The way this technique is done, if you look at any transmission microscope, those who have seen, you can understand very easily. Those who have not seen, I am going to discuss with you in the next subsequent lectures. In a transmission electron microscope, one can use a holder known as a heating holder, so the sample can be heated up at a different rates or very specified by the user, and can be viewed on a continuous mode like a video, and from those videos one can basically obtain the transformation, phase transformation taking place in the material. So, therefore, it is a very easy to monitor, easy to do a technique, and in this technique one can heat up to temperature approximately 1000 to 1500 max. So, nowadays even the holders available which allow you to heat at the rate of maximum 500 degrees per second. So, therefore, immediately you can heat up the material, look at what is happening by passing all kinds of solid state transformations. So, this is a very advanced and very useful technique used in many material scientists to understand the basic behavior or basic phenomena taking place for any material, especially used on nanomaterials, like how the nanomaterial grows, how the nanomaterial transformation takes place in a system like alloy, which I am going to discuss. So, for this purpose, I am going to show you also how different techniques can be used. So, here I am going to give an example on lead tin, which is very low melting eutectic alloy particles size below 100 nanometers embedded in an aluminum matrix. This is basically prepared by a route called melt spinning, in which aluminum along with lead tin alloy was melted, and because lead and tin are immiscible with aluminum, so therefore, there will be liquid phase separation, and if you rapidly solidify, this can lead to the small size nanoparticles. The left side of the image shows you an image for using HARDIF, that is high angle annular dark field image. This is also attached with the transmission electron microscope. Normally, this gives you images based on Z contrast, that is the atomic number contrast. Just like in ACM, we can get atomic number contrast using backscatter electron imaging mode. Here, we can get atomic number contrast using HARDIF imaging mode. In fact, this can be used in high resolution mode also to see different type of atoms in the high resolution images. But we are showing you normal wide field image using this detector, which is attached with the transmission electron microscopes. What you can see here in this image is the black background, which is basically aluminum, low atomic number elements, therefore, it will be seen as a gray or black, on which there are nanoparticles like this one, or maybe this one, or different sizes. Each nanoparticle shows a double contrast or two phase contrast, one at the top, one at the bottom, or vice versa, depends on how the particles are oriented. You can clearly see the different contrast in all the particles existing. That clearly tells that there are two different kinds of phases. They have two different types of atomic numbers or average atomic numbers. So, therefore, by using this technique, one can easily map the whole microstructure using Z or G or atomic number contrast. If we do normal electron or wide field microscopic imaging, one can see these particles which are very small, about less than 100 nanometers, and it contains lead and tin within the aluminum matrix, where tin is the bulk part of this particle, lead is forming the cap. So, by knowing this, one can understand the morphology, orientations of this particle with respect to the aluminum, and many other stuffs, which I am not going to discuss in detail, but these are all available in the published literature. If you just do a normal diffraction scanning calorimetric analysis, which is not part of the syllabus, but probably you have heard of it. This technique will tell you if you heat or cool a sample, if there is a phase transformation taking place or not. Here left hand side is basically, or the y axis is basically power, and x axis is a temperature varying from 100 to 210 degrees Celsius. That is how the lead tin normally melts, eutectic lead tin particles. So, if I heat it, which is shown by red curve, you can see the melting peak, which is very convincing to us. That is a strong melting events, but once you cool it down, the solidification does not take place at a fixed temperature or range of temperatures. It takes place at a wide range of temperature. Even the solidification peak is also very diffuse. So, it tells you a lot of different stuffs or different aspects of the whole melting solidification behavior, which is can take longer time to discuss. But what you understand is the melting is very sharp, and there is a melting events before the melting event. There is something happens here, that is why the peak is asymmetric. So, to understand it, we put the sample inside a microscope or a heating stage microscope rather, and heat it up. I am showing you a set of dark field images which will tell you how this can be used to understand the phase transformation. If you start from room temperature to 90 degrees or even 145 degrees, nothing much happens to the particle. The dark field image basically taken in such a way the lead part is illuminated of the particle, tin part is not. Please do not get confused from the earlier picture. This is just to orientate so that we can understand the process, and this vector G is used to image the lead part of the particle. If heat from room temperature 90 degrees, the small adjustment of the phase mixture takes place because of the eutectic phase diagram. 145 degree again little bit adjustment. The most notable thing happens at about 170 degree 1 degree Celsius temperature. These temperatures are obtained from the heating holder. Heating holder will have a thermocouple attached to it, and this thermocouple will sense the temperature. Therefore, heating holder cannot really sense the temperature of the sample, but it can sense the temperature of the furnace. So, there will be some temperature difference between the furnace and the sample, but we do not bother much because we cannot measure the exact temperature of this nanoparticle by putting a sensor, which is not possible till today. At 171 degree Celsius temperature, the whole particles become lead rich. So, therefore, a eutectic particle which is consisting of two phases transform to a single phase particle before even it melts down, and then melting begin at 178 degree Celsius temperature. Part of the particle is already molten, and about 82 degree 182 degree Celsius temperature whole particle is molten. So, therefore, the melting temperature particle almost remains same. We know that lead in eutectic melts at 182 degree Celsius temperature, but the whole particle does not melt like eutectic, which has been reported in the literature. You do not need to bother about the basic things inside it. What you need to understand or want to need to know is that by using this in situ technique, we can probe even how a small size particle, which is approximately 100 nanometers, can be understood. So, therefore, we need to have this advanced characterization techniques to be used in the day-to-day lifetime to know this. And this is again to show you that this is the case the particle transformed to single phase lead rich solutions. This is wrong. This will be lead rich solution before even melting. The third one, or the last example which I am going to give to you is on wear performances of nanocrystalline copper lead. We know that copper lead alloys are very important because they are used in the bearing material. They are actually bearing material for many of the objects or the machines we use because of the anti-friction and the lubricating properties of the lead, which is normally obtained by preparing a copper lead composites, because lead is normally very low temperature. Yeah. So, essential requisite for bearing application is that it must have a duplex microstructure with a homogeneous distribution of this soft lead phase, and hard matrix in which the lead is embedded is basically provides the wear and the resistance, and also the helps the lead particles to perform as a lubricating ones. So, normally this can be done using casting techniques. The samples can be prepared, but casting techniques leads to inhomogeneous microstructures. Many cases this also leads to some kind of lead, big particles of lead inside the samples. So, that is why sintering is adopted, and if you want to use a normal sintering technique, it can takes you very high temperature, about 500 to 900 Celsius temperature for a long time to obtain good sinter products. So, we have not used that. In our study where we used a technique called Sparks plasma sintering technique, in which the sintering can be done at 3 to 400 degrees Celsius temperature and also at a time limit of 20 minutes. So, therefore, one can actually form the nanocrystalline copper grains structure during the sintering process because of the use of low temperatures, and so the time used in this technique is low. So, these are all published in the different literatures. What I am going to show you some use of characterization techniques. The first one is use of scanning electron microscope, which is shown here. This is the backscatter electron images of the copper 10% lead, copper 12.58% lead, and copper 15% lead. And all the cases you see the white color things are lead because this is a high atomic number, the gray contrast is from the copper, and you can clearly observe the uniform distribution of lead in the copper. This does not tell us whether copper grains are nanocrystalline or not. To understand it, we go for the time electron microscopy, where we can see that these grains are indeed approximately 100 to 100, less than 100, or even some cases 120 nanometers, and lead can be seen between the two grain of the copper or at the gain junction point, triple junction points. One can observe even lead particles which has fallen off during TM sulfuration. So, these two techniques using scanning tunnel electron microscopy and also time electron microscopy, we can see both the lead distribution as well as the copper grain size. Now, if we understandably, obviously it has a very good distribution of lead in copper. With the nano grain copper, we will have very good friction properties. That is what has been done in this case. You can see the coefficient of friction can be as low as 0.4 in all the cases, and by showing it, we can say that the frictional property of the material has improved. But how? To understand that, we have looked at the wear surface in SEM or scanning electron microscope. One can see different kind of things. One can see delamination, one can see even the breakage of the particles by using the scanning electron microscope. Even if you use the EDAX, that is the electron spectroscopy, energy dispersive spectroscopy by using electrons in the scanning electron microscope, we can see the peaks coming from iron, oxygen, copper, lead, even iron is very predominant because we used the iron ball or the steel balls for abrading the surface. So, iron comes into picture and forms a Tibor layer. Not only that, to even understand that how the oxygen is affecting the microstructure wear process, we can use Raman spectroscopy. Very small size laser beam can be focused on the sample and the Raman peaks can be obtained. This shows us presence of Cu2O, Fe2O3, lead oxide on the surface. Therefore, oxidative wear takes place on that. To clarify it, even one can do vacuum wear test and then map the elements using electron microprobe analyzer. If you see that the oxygen presence on this sample which is tested in vacuum is very small, on the other hand tested in air, oxygen signal is very high. The other signals are copper and lead, so which will be present predominantly on the sample. This is another important techniques like electron microprobe analyzer, which is using a Pessel gun like focus the field emission gun can give us a very high resolution. Then one can actually look at subsurface imaging using focused ion beam. In this technique, sample is dig, a trench is made and the sample, and the surface inside this trench is seen either on an ion beam to show the cracks or the different particle present, or on a scanning electron micrograph like that, where you can see these copper grains or agglomerated copper grains, lead particles. Even some of the lead particles can be seen to be fractured, steps to be formed, and some cases they are sintered. You can see some cases they are sintered actually here. So, therefore, all kinds of phenomena can be easily observed if you look at the subsurface imaging using focused ion beam. This is again shown here how different particles has been fractured or steps has formed or sintered. So, in summary, what I can say you is this, that we need to use different advanced characterization techniques to understand the phenomena taking place during processing. Third illustration, or the last one in this class, in this lecture, is on wear performance of nanocrystalline copper lead alloys. We know that copper lead alloys are used extensively in bearing applications, and this is done for a long time because of the anti-friction properties of lead, also self lubricating properties of the lead within the copper. Copper and lead are immiscible in actual sense in solid and liquid state. So, therefore, they form very nice distribution of the lead in the copper. Normally, for any bearing applications, we know the material must have the following requirements as far as the microstructure is concerned. It must have a duplex microstructure. We know that for bearing application, the materials must have following microstructures or requirements. First of all, it must have a duplex microstructure consisting of homogeneous distribution of the second particles like lead here in a matrix of copper. The matrix actually resists the wear, becoming harder, and the soft phase, which is the lead here, which can act as a lubricating agent, thereby reduces the wear and tear. So, it has been seen that copper lead alloys can be prepared by casting routes, and this routes leads to inhomogeneous distribution of the lead in the copper. That is because lead is immiscible with copper, and that is why the distribution of the lead in copper will be very bad because of the different problems in the casting techniques. That is why no one uses normally the casting route to prepare copper lead alloys, rather use sintering techniques or the powder metallurgy techniques. In the conventional sintering routes, where copper and lead powders are mixed and then sintered by pressure-less technique, it has been observed that it takes about 500 to 900 degrees Celsius temperature by heating the sample or the powder mixture for about 6 to 10 hours to get dense sinter product. And this temperature and the time obviously will lead to extensive grain growth of the matrix or copper, and also it can lead to oxidation of the both copper and lead. So, that is why nowadays one can use special techniques to stop the grain growth for keeping the nanocrystalline copper grains in the microstructure, at the same time to stop the oxidation. Both are required for better performance of the material. This can be done by using a special technique known as spark plasma sintering technique, which is a very recent one, which has been developed in 90s and hardly about 20 years old. So, this can allow us to use lower temperatures of 3 to 400 degrees Celsius temperature for sintering of copper lead alloys, and the whole sintering cycle can be finished within 10 minutes. So, therefore, it will stop the grain growth because of low temperatures and time, and also because of less time at high temperature, oxidation can be reduced. In our case, we have used these techniques to prepare the samples. Then we have analyzed the sample using different characterization techniques, so that we can understand the wear behavior of this material. First, I will show you the initial microstructure. Here I am showing you the microstructure of the copper lead alloys with different lead concentration 10, 12.5 and 15% lead. What you can see is these white phases, some cases they are discontinuous, and some cases they are particles, they are actually lead. These images are obtained in scanning electron microscopic image using back scatter electron mode, which we will discuss as a part of this course, which can show up the Z contrast or the atomic number contrast. Lead having the higher atomic number will be seen as a white. So, lead is uniformly distributed in all the samples, as you can clearly see, and copper can be seen as a gray contrast, but grains of the copper cannot be seen in the SEM, they are very small. To observe the grains of the copper, we need to see the samples in transmission electron microscope, and these are the two images taken from transmission electron microscope of the copper lead sample. You can see the grains are very small. This is the 100 nanometer bar, so approximately 100 to 120 nanometer. some cases even lower than 100 nanometers grains can be seen, and lead particles are seen to be situated between the copper grains, many cases between in the triple junction points of the grains, or some cases lead particles has fallen off during TM sample preparation. So, therefore, by using both the scanning electron microscopy and the time electron microscopic techniques, we can understand the microstructure very well, and by seeing the microstructure you could probably understand that this is a very good material for wear resistance study. This has been done using the fretting wear technique, and here I am showing you some coefficient of friction values obtained by our study. You can see that for different concentration of the lead 12.5, 15, or this is also 12.5, but at different hardness. So, what you can see that the coefficient of friction is pretty low as compared to copper. Coefficient of friction of copper is about 0.8 against steel, and this wear test is done using a steel ball on a fretting wear machine. So, because of that the coefficient of friction is, because it is low, that means lead has a predominant role reducing the coefficient of friction. Not only that, the hardness of these materials are pretty high, as you can clearly see, because of the nanocrystalline copper grains. So, now how the characterization techniques can help us understand the wear process. Here I am showing you the wear scar during the fretting wear at a low magnification picture, which is approximately about several millimeters, because this is 0.1 millimeter. So, therefore, it will be approximately several tens of millimeters, and within that if you just look at in zoom view, you can see delamination, you can see even cracks, some cases you can even see the lead particles spread across the sample. So, if you take a EDAX of this surface, the EDAX means energy disparity spectroscopic technique attached to the SEM, you can see presence of oxygen, iron, copper obviously, and lead. Iron is predominantly present there. This is because iron is getting transferred from the steel ball. Oxygen is also present. Therefore, what is the exact role of oxygen? One needs to understand very clearly. That to do that, we have done Raman spectroscopy on this wear sample or the own surface. If you do that using a laser beam of 540.53 nanometer with a very small laser power, one can see presence of lead oxide, copper oxide, iron oxides on the surface. Therefore, oxidation do take place on the surface because of wear, but one can easily prove it even using a better technique known as electron microprobe analyzer. Here we have done wear test in vacuum, wear test in air to see the oxidation. If you use electron microprobe analyzer in a fake EPMA, that is the field emission gun EPMA, where the beam size is very small, resolution will be better. So, you can see the oxygen is very small even on the surface for the sample tested in vacuum. On the oxygen is quite large in the sample tested in the air. Copper and lead are obviously present on the sample, and this is the SEM image of the sample on which this EPMA analysis is done. So, therefore, by using these two techniques, Raman's and the EPMA, we can clearly see how the oxidation takes place. Oxidation does takes place during the wear process and changes the wear kinetics. In order to look at this subsurface deformation characteristics, one needs to use another kind of characterization technique, which is known as focused ion beam, to prepare the sample. So, what you do, take this wear track and cut in metal and make a trench. We can do on at different actually wear surfaces. This is shown in the next figure. Here we have made a trench cut using focused ion beam or the gallium beams in the focused ion beam machine, and if you just tilt the sample and view even in the focused ion beam by using the ion beam contrast, one can see even different black color things which are basically particles. You can see even they have cracks which is going like this. Better image can be obtained if you see this trench in scanning electron microscope. You can see the lead particles peak white color and also the copper agglomerated grains. Leads are seen to be fractured in many cases, some cases steps to form on the surface of the lead, and some cases leads are small size particles, some cases they are agglomerated because of the sintering. So, therefore, during whole wear process, temperature do rise in the subsurface domain of the sample and leads to the sintering, and during deformation some of these lead particles do get deformed and steps forms on the surface and fracturing also do happen. So, this is again shown here in a very high magnification picture with insets. So, this you can see very clearly. So, what I am trying to convince you is that by using this set of characterization techniques which are known as advanced characterization techniques, we can see the surface, subsurface of the sample during wear process and understand the wear mechanism very easily. So, in summary and also for the subsequent lecture, I am going to say you something here, that in summary I can say that we need to use advanced characterization techniques for not only to understand the material science phenomenon in a particular process, but also to understand the processing techniques which are used or required for the whole material science domain. Many cases we need to engineer the material, and engineering the material means changing the processing parameters, changing the sample characteristics, sample compositions. How does these parameters affect, how do these parameters actually affect the processing and the material properties later on can only be deciphered if you look at the samples using different characterization techniques. And these characterization techniques can be either microscopic techniques as we have seen, or it can be spectroscopic techniques. Many cases we need to use even diffraction techniques to understand the processes, which I have not shown you in the first lecture, or many cases even one can need to use the surface characterization techniques like the Auger electron spectroscopy or any other spectroscopic techniques which can give us surface properties. This is more important for the particles which are very small size like nano size or even some cases micron size. So, therefore, in a nutshell what I can say is that we need to know in detail the detailed characterization techniques which are used or which will be used by many of these labs for understanding the material science phenomena. So, in the next class I am going to start with microscopic techniques will be used to understand microstructure. So, therefore, the connecting the microstructure with the material processing can be only done by using different microscopic techniques. This will involve SEM, TEM, AFM, STM as well as confocal microscopy. We will discuss one by one these techniques. I will first start with TM in the next lecture, then move into SEM, and finally other techniques will be dealt with. Thank you.